I was willing to say that. I just
Okay. Oh, sorry.
I know I can do it in Python. I know how to use it.
Competitions were always
But
When we take some questions.
We haven't covered, so we've done 1, 2, 3.
I think we'll go ahead and get started. Welcome everyone to Tools and Technology Seminar Series. I think you've all been here before, so I don't think I need to give you really much spiel about the seminar series. There's a sign-in sheet going around. Please remember to sign in. It just helps with the pizza and lets us know how many people came so that we can justify the pizza. I sound like a broken record, but I am looking for speakers for next semester. There are a few gaps in the schedule right now that I'd like to fill, so if anyone's interested, please let me know. With that, I'm pleased to introduce our speaker. Today we have Xinqiang Ding from the Brooks Lab, and I'll let him.
Hello everyone. First, thank RC for organizing this presentation and Alex for the technology support. And thank you all for here, a special lunchtime. For those of you who don't know me, I'm a fourth-year PhD student in bioinformatics department. I work in Brooks Lab, which is in chemistry building. The work in our lab is mainly focused on using molecular simulation or molecular dynamics to study how protein moves, how protein interact with another protein, and protein-ligand interaction, like drug design, kind of thing. So today I will talk about the project I have done in the last year, which is accelerating protein-ligand docking using FFT on GPUs. So as you can see, there are three keywords over here. One is protein-ligand docking, one is FFT, which stands for fast Fourier transform, and we make it work on GPU to make it faster. Okay. So before I dive into the details, I want to give you some background because in our even though we are in the same department, we sometimes don't know too well about what other people are doing. So first is about the protein-ligand docking. Imagine this, you have a protein and you know the structure of the protein and you are giving a ligand. So what you want to know is two questions. As if this ligand binds with this protein, and if this ligand binds, how is the binding affinity or where it binds? So to answer the question fully, we need this quantity called binding free energy. Because this quantity really captured what is going on in this binding and unbinding process. But this binding free energy is, even though it is captured fully of the process, but from the computational standpoint, it's very difficult to calculate this accurately. Even though in the last decades, I would say, in our field, we have made a very large progress toward to calculate this quantity. But this is, generally speaking, this is very difficult to get. So what do we should do if this is difficult? Another thing to say is the reason this is difficult because if you remember from your PChem class, the delta G is equal to E minus Ts, which has an entropy part. So that the entropy part is very difficult to calculate. So that's the reason why this is difficult. So the approach we have in protein-ligand docking is instead of calculate this quantity directly, we make an approximation to design an energy function to approximate this quantity. Hopefully, we can recapitulate what is happening in the binding process. Okay. Generally, in a docking methods or docking algorithm, there are mainly two parts. One is energy function, which is approximation to the binding free energy. The other one is a search algorithm, because we assume that the binding poles will corresponding to the poles with the lowest energy. So we need two parts, energy function and search algorithm. So what kind of energy function have we used? Not we, but in the field, in the protein-ligand docking field. One kind of energy function is physics-based force field. The most well-known one is charm force field, which is we used in our lab, and another one is amber force field, which is used in AutoDock, which is a very popular, well-known open source docking algorithm or docking software, widely used. Some other energy function is like empirical energy function, which is learned from protein-ligand docking database. For example, X-score and Chem-score are well known. And the third class is like knowledge-based, like the drug score, which is you analyze all the drugs that is on the market and to see if they have some special property. So you can design score for that to quickly screen the compounds you have. So a little bit about the force field we use. As you can see, we use this charm force field. So these two are quite similar in terms of the formula, but they are different in the parameter. So in our force field, or in generally in molecular dynamics, the force field we use is like this. So this is the potential energy U is equal to, this corresponding to the bond energy. So you have two atoms, have a bond between them. So you will have bond energy, which is a harmonic oscillator approximation. Because the bond energy is so strong, so usually it doesn't break. Usually it's just oscillate around the equilibrium position. So this is the reason we use the harmonic oscillator. The same as the angle. When you have three atoms, you will have angle. So this is the energy corresponding to this angle. And this is a torsion angle, in which case you have four atoms. It's like the angle between two planes. And this is corresponding to the van der Waals interaction, which is a non-bounded interaction. And this is corresponding to the electrostatic interaction. So the most difficult part to calculate, or the most time-consuming part to calculate, is these two parts. One is van der Waals, the other one is electrostatic interaction. So why? Because if you count how many terms are here and how many terms are here, they're about n squared. If in your system you have n atoms, the term over here will about have n squared. So which means the time complexity of this evaluation is increased according to n squared as you increase the number of atoms. The same over here. But over here they are linear. So most of your computation time will spend on this part. Okay, this is the force field we use. Another part, as I said, in the docking, protein-ligand docking algorithm. Yes.
In your previous slides, so do you take a hydrogen bond into just as a non-bonded pair?
Yes.
But does the hydrogen bond energy they follows that rule? Or?
It's like this. It's the development of force field. At the beginning, they have a specific energy term down here corresponding to hydrogen. But now, as the force field moves on, or in the new development, we just don't treat hydrogen bonds specifically. We just use non-bonded interaction for that. Yeah.
And also, when two atoms comes too close, they have clash.
Right.
So
that will correspond to this part. They can't come too close, right? You have this will be really high because inverse 12 power. Okay, another part in the protein-ligand docking is once you have this energy function, you want to find the pose that has the minimum energy according to this formula. Right, so you need a search algorithm. So in order to appreciate how hard the problem is, you need to consider how many degrees of freedom we have. Let's say you have this protein fixed, you have this ligand, and you want to dock this ligand onto the protein. If you assume the protein is rigid, the ligand is rigid, you only have this 6 degrees of freedom, which is corresponding to translations and rotation, right? So this will be easier, but the reality is not so simple, because when this ligand binds into this protein, the ligand can change. They are flexible. So if you add in the ligand conformation in the search, it will increase the number of degree of freedom to a large number. So for a relatively medium size ligand, it can easily have 10 or 15 number of rootable bonds. So which means the degree of freedom will increase by 15. Another more challenging problem is when the ligand binds into the protein also changes. And there's the degree of freedom over here is overwhelming. It's like in your protein, the side chain can move if you assume the backbone is fixed, but there are too many side chains, even though it's just around the binding pocket. So because we have so many degree of freedom, we already have some heuristic search algorithm instead of solve the problem exactly. We can't do that. So usually people use Monte Carlo for similar annealing or molecular dynamics for similar annealing to search the lowest energy. Another popular algorithm is genetic algorithm, which searches the minimum energy pulse, which is quite effective. Okay, any questions so far about protein ligand docking? This is the background, I guess. No? Okay, let's move on to this Fourier transform. So why these two things are connected? I'll give you very simple about this discrete Fourier transform, which is the Fourier transform on the discrete set. So just give you some very simple example, what it is, and what it is used for. So the definition is very simple. Like you have a original signal f. It's a vector of length n, and you want to calculate this Fourier transform capital F, which is also a vector of length n. So why would you want to do that, you may ask. There are many reasons you want to do this, so I won't go to the reason. So basically you want to do this calculation. It's very useful for all kinds of purposes. So if you look at this, this is like it's nothing more than a matrix times a vector. So this is capital F. This is the original. So if you do this calculation, it's the equivalent to do this calculation. And this is the transform matrix. So it's like this. This is your result. This is what you want to calculate. This is the input, and this is the transform matrix. So if you calculate how many computation you need to calculate this capital F, you will need about n to the square number of computations, because you have to use this times this, sum them up. Use this times this, sum them up. So you will do n squared calculation. It will usually take n to the n squared time. In general, if the matrix is an arbitrary matrix. However, because this is a Fourier transform, this matrix is very special. So this is the reason you can design an algorithm to do the calculation, play some tricks, I would say, to calculate the f, which is basically a divide and conquer algorithm. So what they did is, if you calculate this naively, you will need about n squared time. If you use FFT, you will need n log n time, which is a huge increase, I guess. In computer science, if you have algorithm into n squared, it's usually not good enough. If you have n log n, it's blazing fast, I guess. So how they do this, you can Google it. There is a lot of thing about it, so I won't go to the details. And also, if there is one algorithm you need to know or you want to know, this is, I guess, the most well-known and most useful. It's one of the top 10 algorithms in 20th century. So, and a lot of digital stuff rely on this algorithm to work. The music you listen, all kinds of things. So why are we interested in the FFT and what it is useful? I just give you a simple example where we can use FFT to accelerate our calculation. For example, you want to calculate, you are given two signals. One is F, one is G. They are very general signals. You can plug in whatever quantity you are interested in. And what you want to calculate is this cross correlation H between F and G. So the definition of the cross correlation is like this. The cross correlation is also a vector of length capital N. So at each position N, Hn is equal to this formula, which basically corresponding to you have two signal F and G. The cross correlation is you just shift it, offset by a fixed amount, which is N, right? Then you multiply the corresponding term and sum them over, which is your cross correlation. This is some quantity that in many applications, they want to calculate this quantity. So how would you calculate H given this F and G? Well, you can do this naively, right? So you can write a for loop for small n from 0 to n minus 1. You calculate this, so you return, right? So if you calculate how many calculation you did, you will say you did n squared calculation, which means the algorithm, the time complexity is n squared. So this is where the FFT can come in. So this H cross correlation is equal to this quantity, and we have a symbol for that. It's F star G. So the trick we played here is we take the Fourier transform on both sides. Okay, so this side will become Fourier transform of H and Fourier transform of this F star G. Okay, and the Fourier transform has a very nice property. Oh, another thing is F star G. The cross correlation is, you can also view the cross correlation as a convolution between two signals, except you just reverse one signal. So basically, you take the Fourier transform. The Fourier transform of H is the Fourier transform of the convolution between F and G. And the Fourier transform has a nice property that the Fourier transform of convolution between two signals is equal to the product of the Fourier transform of each. Okay. Now what you do is at the end you will this quantity Fourier transform is equal to, this is conjugate, so you don't you can just view this as the product of two Fourier transform. Okay. So now we play the trick. We use we do an inverse Fourier transform. So on the left we will get H back. On the right we just do whatever the inverse Fourier transform did. Okay. So now we can calculate how many calculations we need to calculate this H vector. So you see in this part, because I already told you that the Fourier transform, one time Fourier transform only takes n log n time. So over here, it will take us n log n time. Over here, it will take us n log n time. Then that's it. So, right? So if you calculate this way, you will need your n log n time instead of n squared. This is why it is useful. It can accelerate a specific calculation or specific quantity you want. Okay. Any questions so far about FFT? No? Okay. Then how is FFT related to docking? So this has a long history, not quite long, but the first application of FFT in docking is in protein-protein docking. And in this 1992 paper. So the problem they solve is a rigid body protein-protein docking. So you have one protein A and another protein B. You want to dock them together, and you assume that both proteins are rigid body. So you only have 6 degrees of freedom. So what they did is they make a grid. So for protein A, you have a vector, 3-dimensional vector A. The value of the vector at each point is like when you have this protein, you make a grid around the protein. Okay? So at each grid point, you assign a value to it. The value will be equal to 1 if the grid is on the surface of the protein. It will be equal to 0 if the grid is outside the protein. It will be equal to 0 if the protein is if the grid point is inside the surface of the protein. And this 0 here is a negative number, small negative number. And you did the same thing for the protein B. Okay, so it's like this. You have two protein A and protein B. You assign this A and B vector for each protein. You see the white here corresponding to 0. The black, you can see the black around the surface corresponding to 1. And the gray inside the protein corresponding to a negative number. Now, in order to dock these two proteins together, you only need to calculate one quantity, which is this C, which is a cross correlation between A and B. So if you calculate this quantity, and the value of this quantity at alpha, beta, and gamma is equal to this, you can see this is the cross correlation evaluated at alpha, beta, gamma. Alpha, beta, gamma is the offset. It's like the n in the cross correlation I showed you in the 1 dimension. Okay. And they assume that the binding pose corresponding to the pose that has the highest cross correlation. Because if your result is like this is protein A, this is protein B. So what will be the cross correlation between, in this case? What will be the cross correlation in this case? This corresponding A term times the corresponding B term. Because they are not touching each other, so every term in this protein A will times a value 0. The same thing for the protein B, which means the cross correlation in this case is equal to 0. And the cross correlation for this case, you can see these two proteins are docked. They will have a positive number for this cross correlation, but that positive number will be not very large compared to this one, because it only docks well for a small set of the surface compared to this one. If you calculate the cross correlation for this one, it will be a large positive number. And in this case, there is some collision. If you have collision, you will have the term that 1, this 1 over here, times the 0 here. The 0 is negative, which means if you have collision, it will decrease your cross correlation. So which means if you set up the array like this, your bounded pose is corresponding to the pose that has the highest cross correlation value.
So, I have a
Yes.
quick question. So, I'm sure, like in this paper, they have done comparison with like native contacts or from crystal structures. Has it ever happened that the pose that they found has a higher score than the native contact? Which means, does nature always maximize this? Just curious.
You mean they find a pose that should be a
So
false
it's always
positive
the highest. I mean, yes, like highest cross
than the
correlation.
native? I'm not sure. I would guess it could be possible for that. But the native pose should correspond to a local maximum. So if you plot the cross correlation in respect to alpha, beta, and gamma, you will see some peak, okay, which corresponds to the local maximum. The native pose should correspond to one of the local maximum. Yeah, not necessarily for the highest one, I guess.
So here they only assume, so they think the reason the two dogs is only because of shape complementary.
Yes.
It has nothing to do with hydrophobic interaction or electrostatic.
Yes, we will consider electrostatic later, but in the first paper they only consider the shape complementary. You're right. It's only consider shape, which basically only consider the van der Waal. Okay, I will introduce you for the protein-ligand docking and the FFT and how they are related. Let's go to what we have done in the past several months is we use the idea FFT to do the protein-ligand docking. As he said, in this one, they only consider the shape. They don't consider the energy. So basically, this is an approximation. So what we did is we express the non-bounded interaction energy, which is electrostatic interaction energy and van der Waal interaction energy, as a cross correlation between the protein and the ligand. And once we have done that, we can use FFT to accelerate that calculation. Okay, and we do this. We find a way to do this, and also we implement the algorithm on both CPU and GPU. And see really speed up. And also we compare our new algorithm with previous one on benchmark set. So what we did is like this. As I said, between the protein and ligand, there's only non-bounded interaction, which has two terms, which is it's like the non-bounded interaction is corresponds the sum over all the ligand in all the atoms in the ligand, all the atoms in the protein. And the non-bounded interaction includes the electrostatic potential energy and the van der Waal energy. And if you plug in the formula at the beginning, you will find it's like this. So it's sum over the energy of the ith atom in ligand. This number sum over the van der Waal energy field for the ligand for the atom in the ligand. Alright. Okay. So I would go through some example. Take the electrostatic potential as an example. How we express the energy as a cross correlation between the protein and ligand. Okay. So you see, this is electrostatic energy for the ith atom in the ligand. Right. So the energy, for example, for this atom in the ligand, it will feel the electrostatic force for all the atoms in the protein, right? So it's a sum over all the electrostatic interaction for all the atoms in the protein. And this is the charge of the ith atom in ligand, the GS atom in the protein. And you can put the QI out of this formula like this. So, and you write this as this, which corresponding to the energy, the ith atom in the ligand field is equal to the charge of this atom times the electrostatic potential at that point. They are separated. This QI here is the charge of the ligand. This electrostatic potential only depends on the protein. So what you do here is you find the binding pocket, you make a grid. So at each grid point, you calculate the electrostatic potential. This VE here, okay? And if an atom is sitting on this grid point, the energy the atom feels will be equal to QI times VE. Okay. It's actually quite simple. It's just the energy is equal to the charge times the potential. Okay. One problem with this is what if the atom is sitting instead of exactly on the grid point, it's inside of a unit cell. Okay. How would you calculate the energy? We use a simple trick called trilinear interpolation. Like this. You have the electrostatic potential on all the points for a unit cell, and you want to calculate the electrostatic potential of a point inside the unit cell. So what we do is we use trilinear interpolation, which basically you use a linear combination of all the points to approximate the energy potential of this point. And the coefficient depends on the distance of this point to the left wall, the bottom wall, and the back and front wall. Basically, if this point near this point this grid point will have a larger weight in the linear combination. And we do the same thing for the ligand. So here is for the protein, because this electrostatic potential only depends on your protein. Once you have the protein, you can calculate this. Now you can do the same thing for the ligand. So let's say you have an atom for the ligand at this position, and it has charge Qi. So what you do is you distribute the charge onto this grid point. Okay, basically you just divide them up and put part of it at this point, part of it at this point, part of it at this point. Okay, and how much you put here depends on the distance between this point and this point. If it is closer, you put more there. If it is further away, you put less charge there. So after you do this, you will find that the energy, this is the electrostatic energy of the ith atom in the ligand, for the ligand, is equal to the inner product of this Q, charge distribution, and this electrostatic distribution. So it's a cross correlation, I would say, between two vectors. Basically, what I did for the 3 slides is we find a way to represent the electrostatic interaction as a cross correlation. It's like this. The procedure is like this. This is the protein, the binding pocket, and you put a grid around this binding pocket, and you calculate the electrostatic potential on the grid. And given a ligand, you do the same thing. You distribute the charge of each atom onto the grid point. Okay. Now the energy is equal to, if they overlap like this, the energy will equal to this, which is inner product between these two vectors, right? But as I said, the ligand can move around the binding pocket, right? So like this is the ligand. The ligand is red, so the ligand can move up by 1 unit of the length of the unit cell. Then that corresponds, the energy of this pose or this position is equal to the cross correlation evaluated at 0, 0, 1, which means this one here means you move the ligand up by 1 unit. And you can move it around y direction as well. The energy will be like this. So you can do generally, the ligand can move 3-dimensionally for every point. But the energy is always a cross correlation. So if it is, because it is a cross correlation, we can play the trick we played in the 1-dimensional case, which means the energy corresponding to all possible translation on the grid is equal to a cross correlation between two vectors. Basically, it's equal to a convolution between two vectors. If you do this naively, it will take about n to the 6th power because you have 3-dimensional now. Each dimension has n point. So we play the trick. We take the Fourier transform on both sides, and we take the inverse Fourier transform on both sides. Then we can get this u back by just doing this amount of work. So basically, you do this naively, you take 10 to the 6th power. If you use FFT, it will take into the 3 power log n, which is a very big speed up. Okay. And this is the electrostatic energy. Another thing is we have van der Waals as well, right? So it works almost the same for van der Waals, except it's more complicated. So I won't show that because it needs, instead of 2 grid, you need a set of grid. So, but the principle are the same, but it's just a little bit complicated. So we did the same thing for almost the same thing for the van der Waals, and it works. So let me show you some benchmark on the running time, how much speed up we have. The benchmark is like this. The grid has size 60. 60 is the number of points along each dimension. Okay, for this grid from the protein, I will call it grid, potential grid. So this is the grid from the ligand. The ligand is smaller than the binding pocket, right? So the dimension is like this. This is X, Y, Z. This is the number of grid points. And this ligand can move around inside of this big grid, right? So it can translate along X, Y, and Z direction. And the number of translation, different translation, is about this number. It's about 60,000. So the purpose here is to calculate the energy corresponding to all these 60,000 positions. Okay. So what you can do is you can write a for loop, again, naively. Okay, you can for loop over all possible translation, and you calculate the energy for each position. I did a test on this kind of CPU, which is already very good CPU. If you do this naively, it will take about 30 seconds to do all the work. But if you use the FFT we just described, it will use about 0.3 seconds, which is 100 times speed up, right? But you get the same result. You get exactly the same thing in this time instead of this time. Exactly the same thing. Okay, as I told you at the beginning, we take a step further. We make it work on GPU as well. So we did the same benchmark. This is FT on CPU. This is FT on GPU, which is about 0.01 second. Here's another 28 times speed up. So I probably should mention that this time is not the time that you run one FFT, because on GPU, the speed up comes from you can run multiple FFT simultaneously. For example, on CPU, you can only run one FFT at a time, right? But on GPU, you can run 100 or 200 at the same time. This is corresponding to like it takes 1 second to run 100 FFTs. So this is where the speed up is. This is giving you some results for the rigid docking. So to make sure we implement this correctly, this is the energy landscape for docking the ligand into the protein. And this is x-axis corresponding to the x position, x coordinate of the ligand. This corresponding to the y-coordinate of the ligand. And as you can see, the picture is changing as you move zoom in along the z dimension. It's like each point is corresponding to an energy corresponding to that position, that pose of the ligand. So x, y, and z. Z is changing. Okay. So as you can see, we can find a local energy minimum. This is where the native pose is. You can see the native around here. We have a local minimum. So this blue point corresponding to the energy that is lowest. It shows how the energy changes as you move the ligand around the binding pocket. So this is for the rigid docking, rigid ligand, protein ligand docking. Because as I told you at the beginning, when you have protein-ligand interaction, the ligand can be flexible. The protein can be flexible as well. But in our previous FFT work, using FFT, it only works for rigid protein and rigid ligand, and also for specific orientation. So, however, we can do the FFT corresponding to translation so fast, which means we can do this for multiple orientations simultaneously on GPU. So we incorporate this acceleration into our previous protein-ligand docking algorithm, which is CDocker. So this is CDocker is the docking algorithm in Charm. What it does is do rigid protein but flexible ligand docking. So this is a previous docking protocol. It's like you give in a ligand, you generate a random pose of the ligand. The random pose corresponding to its conformation. Basically, you rotate the root bond of the ligand. You choose a random orientation, you choose a random position, and you put the ligand inside the binding pocket. Then you run simulate annealing using molecular dynamics. Basically, you heat it up, cool it down, heat it up, cool it down. And at the end, you do energy minimization. Hopefully, once you do this multiple heat it up, cool it down, you can find the energy minimum, at least the local energy minimum. If you find many local energy minimum and you compare them, hopefully you can find the global energy minimum. So this is the previous protocol. This is our new protocol with our FFT accelerated procedure. Basically, what we did is as same as this original CDocker, we generated the initial conformation of the ligand, and we generate multiple candidate orientation of the ligand. Because our FFT only works for specific conformation and specific orientation. Okay. Then we do the FFT search, parallel FFT search on GPU. Right. So for each conformation, you have multiple orientation. You do translational search on each or on all these orientations, and you find the energy minimum. Once you find the energy minimum corresponding to this conformation, you can do an energy minimization quickly. Then hopefully you can find the energy minimum, or at least local energy minimum. So this is some bench result on our docking accuracy. So the red one is what I told you, what will be the docking accuracy if you follow this protocol. What will be the blue one is the docking accuracy corresponding to our new accelerated protocol. So docking accuracy defines as the minimum energy pose as RMSD smaller with respect to the native pose smaller than 2 angstrom. If the RMSD between the minimum energy pose and the native pose is smaller than 2 angstrom, we will say it's docked successfully. It's close enough to do some useful work. Okay. The red one is previous. Blue one is our new docking algorithm. And this x-axis corresponding to how many dock you try. Like generate a random ligand, you dock once. Generate another one, you dock once. This corresponds to how many random conformations you generate. And at the end, you will take the lowest energy pose you find across all the trials. That will define your docking accuracy. So as you can see, we have an increase of the docking accuracy using our accelerated CDocker. Okay, that's it. Thank you. If you have any questions. Yes.
Question. It's not my area, but so I assume that the scale of the grid for the ligand and the scale of the grid for the protein have to be the same.
Yes.
And the number of vertices, it seems, that if those increase, then the performance is going to be affected by that. How do they optimize for the scale of the grid? What's the like the distance between the vertices?
Oh, the space.
Yeah.
Over here, we choose 0.5 angstrom.
Is that just, how do you come up with that?
First of all, you can choose different number and compare the energy, because once you have spacing, the energy is an approximation for your energy. So you can change this and see how your approximation, how well your approximation is. Because if you choose this too small, the number of vertices, as you said, is too much.
Yeah.
That will hurt your calculation. It will take a longer time. But if it is too large, the energy is not accurate anymore, which also hurt your docking accuracy. So we try different, for example, from 0.1 to 1 angstrom, and see how the docking accuracy changes and how the energy approximation changes. Then we choose 0.5, which is a compromise between these two. Yes, good question. Yes.
There's no solvent.
As what?
No solvent.
Yeah, there is no solvent over here.
So why do you think this is a good assumption?
What?
Why do you think without solvent you could still generate a good position?
Well, that's would be your assumption, right? Because you want to generate a model, you want to do the calculation, you cannot consider everything, because you want to make, if you consider solvent, you can use, implicit solvent or explicit solvent, which is very time consuming. But the purpose of the protein-ligand docking is to do it quickly, because usually you have millions of compounds. So you want to quickly filter out those compounds that's not binding at all. So you don't have to do extra work on them. So if you want to calculate the binding free energy, like the delta G at the beginning, you have to consider the solvent, right? That would be our assumption.
So in your benchmark set,
yes,
you only showed the RMSD smaller than 2 angstrom.
Mm-hmm.
You didn't show what's the enrichment factor, how well you are able to distinguish correct ligand from incorrect ligand.
Yes, well, I didn't show it. I have a distribution around the energy poles you find. It's like it's not on the slides. Like you have the original docking algorithm, the new docking algorithm, right? You choose the lowest 100 energy poles, and you plot the MSD distribution of this 100 poles.
But all your poles is for the same ligand.
Yeah. No. This is average for different ligand. This is on data set. This is on about 60 protein ligand pairs. This is the accuracy is across all the protein ligand pairs.
So in your benchmark set, what is the portion that are true ligands? They are native ligand of your.
This is redocking. All of them are true ligands.
Yeah. So yes, I think the most important thing of protein ligand docking is for you to screen which ligand is most possible to dock our protein.
Yes, but the benchmark here is not. That is called cross-docking. I understand.
Yeah.
Yeah, but benchmark here is only for redocking.
Yeah.
Which is the basic requirement for your docking algorithm.
Yeah.
If you cannot do well on this, you cannot expect to do well on more difficult problem, which is cross-docking.
Yeah. So what's your performance on cross-dock?
We haven't tested yet. We are planning to do that. We definitely need to do that.
You have shown the number of translation of your method. How about the number of rotation?
The number of rotation. We consider all this docking accuracy is across across all not all possible orientation, across the search down here is not only translation, it's also orientation and confirmation. But we use the FFT accelerated translation in this process.
Only 100 maximum?
No, this 100 corresponding to trials. One trial means you generate one random confirmation of the ligand and you dock it. That's corresponding to one trial. And generate another one, dock it, second trial. And at the end, you will, because one trial will give you a low energy pose, and its energy. At the end, you combine all the energy pose from all the trial and choose the lowest energy one, which is as the final docking pose. Yep.
For testing this, you said you generate random conformations in the beginning for a given ligand.
Yeah.
So I'm guessing this would depend on the starting conformation, right? Because if you have your native ligand and then you generate 100 conformations, you find the lowest energy. That would have some dependence on your starting conformation.
No, you just random rotate the rotor bond. Doesn't depend on the starting conformation.
So you enumerate all possible choice.
No, not enumerate. You cannot possibly enumerate them. You just find the local minimum. Basically, you can do is you're giving the ligand, you do similar annealing for the ligand in vacuum. Then you can find many energy local minimum for the for the ligand conformation, and you dock this ligand conformation.
Why does that but shouldn't that be dependent on your initial conformation if you do simulated annealing?
If you do multiple times, each time will give you a local minimum. This should be different.
But it still depends on your initial conformation, right?
Oh, after a long time, it will forget. So basically, you start from one starting structure. If you hit the temperature is high enough, the end local minimum doesn't depend much on your starting structure.
How do you test it's not dependent?
Or you just run it 2 times, you get the same. you just run it from the 2 different starting structure. You get the same set of local minimum. You can see, yeah, that's it.
Is that how you generated these?
Yes. That's not very much better than the random, actually.
Okay.
Yeah. Work.
So I was also curious about this might be not very okay. So if you generate like different conformations and then you find like the energy for each of the 100 conformations, is there dependence on like the RMSD with the native ligand? So I understand that you're generating rotations and translations, everything of the initial, and you dock,
yes,
and you get some energy. How is that different from if you just take the native ligand and then just dock?
Well, what do you mean you just take the native ligand?
So you don't perform all this rotations of the.
You just
ligand.
use the conformation of the ligand,
Yeah,
but you still have to figure out where you put it, the position
so
and the
you get
orientation.
energy when you do that, right? When you just take the native ligand, you get some energy of docking, and then you generate 100 different conformations, and you also generate energy. So what's like the?
That would be quite easy if you know the conformation.
Yeah. I mean, we obviously know because we're testing it, but just saying like, what would be the distribution of like energy and the RMSD to the native of just the ligands? We're not considering anything else.
What I have done is I use the conformation of the native pose, use the orientation of the native pose, only do translation.
Okay.
The docking accuracy is really high. It's about 98. If you use the native conformation of the ligand, you search the translation and orientation. The docking accuracy is also very high. It's about 85%. But over here, we cannot go to 70%, which means once you add in, make the ligand flexible, it's become much more difficult. Yeah, we have done that. Any more questions?